was.
Sounds good. I have the pleasure of introducing Dr. Avi Loeb. He's the Frank Baird Jr. Professor of Science at Harvard University, recipient and a best-selling author. He received his doctorate in physics from the Hebrew University of Jerusalem in 1986 and led the first international project supported by the Strategic Defense Initiative. Subsequently, a long-term member of the Institute for the Advanced Study at Princeton. Dr. Loeb has written 9 books, including most recently Extraterrestrial and Interstellar, and over 1,000 scientific papers on a wide range of topics. He's the director of the Institute for Theory and Computation within the Harvard Smithsonian Center for Astrophysics and serves as the head of the Galileo Project. Amongst his numerous achievements, he is the longest-serving chair of Harvard's Department of Astronomy and the founding director of Harvard's Black Hole Initiative. In 2024, he was ranked number 3 in publication record and impact of research among all astronomers worldwide over the past 5 years. I'd like to introduce Dr. Avi Loeb.
Thank you so much, and it's a great pleasure to join you. I'll present some slides, and then I'll be glad to answer any questions you might have. So let me share my screen, see that it works. Okay. So I will go over some of my latest work and give you sort of a sense of the background. This is a picture taken a couple of weeks ago. I went to a NASCAR car race in Bakersfield, California, because one of the drivers put the image of 3i Atlas and myself on the hood of his car. So that was an interesting experience. And I told him it's a great compliment for me, but not so much for 3i Atlas because it's this interstellar object is moving at least 600 times faster than his car, and we will get to that. So this is another image from the last week that it's of my office. I took out all the file cabinets and they were replaced by a set of 51 watercolors and 2 bronze sculptures of Galileo. The watercolors are of scientists from the past and what they said. And all of this art was made by Greg Wyatt, one of the most accomplished sculptors in the US. And he just was inspired by the scientific work that I'm about to describe and donated those to my office, and we will unveil them in the coming week. So what is the work about, and why did I become interested in looking for extraterrestrials? Well, the fundamental point is that there are 100 billion stars in the Milky Way galaxy, and most of them formed billions of years before the sun, and they, at least a few percent of them, have a planet the size of the Earth, roughly at the same separations. So for us to imagine that we are the only intelligent species that ever formed since the Big Bang is very arrogant, and we better search for them. There are our siblings in the family of intelligent civilizations, and so far we just thought about the universe as cold and lifeless, and finding our siblings will give us a better sense of connection, that some emotional connection to the universe, and we can also benefit from figuring out whether they were more accomplished than we are. We can learn new science, new technologies, if we find their products. Now, Enrico Fermi asked, "Where is everybody?" back in 1950, and that's a question that every lonely person asks. And what you tell a lonely person is, don't be so presumptuous. You are not that attractive. They will not come and sit next to you. You need to search for them. And Enrico Fermi didn't really build a telescope. He didn't devise a spacecraft that will engage in travel and look for them. So the key is to invest resources in the search. And very often mainstream academia argues that it's an extraordinary claim to imagine something like us, but I think it's actually an ordinary claim, because we started from a soup of chemicals here on Earth, and we know that the physical conditions in billions of Earth-Sun systems in the Milky Way galaxy alone are similar to those that started life here on Earth. And it's very reasonable to imagine that something like us existed billions of years before us. And so we just need to seek ordinary evidence for an ordinary claim. There is nothing speculative about it. It's much more speculative to imagine that there are extra dimensions, extra spatial dimensions, because we haven't found any evidence for that. And there is no reason to suspect that there is more than three. And nevertheless, it's now the mainstream of theoretical physics to imagine that there are extra dimensions. So I regard this as much more down to earth than other speculations within the realm of the mainstream of physics. And of course, if we don't search, we will not find anything. Now, the mainstream of astronomy is focused on the search for microbes, in particular, the chemical fingerprints of microbes in the atmospheres of exoplanets. But my point is that technological signatures might be easier to discover. So right now, the highest priority in the astronomy community is to invest more than $10 billion in the next 2 decades in search for the signatures of microbes. And I would argue that we should hedge our bets and invest similar level of funding to the search for extraterrestrial intelligence as we do for microbes, because it's very challenging. Even if we find oxygen, methane, and other molecules in the atmospheres of exoplanets, some of them can be produced by geological processes, and it will be an ambiguous detection. Whereas if we find a technological gadget in the solar system that came from another civilization, or we detect artificial lights on exoplanets, on the night side of exoplanets, or we detect industrial pollution in the atmospheres of exoplanets. These would be signatures that are very prominent potentially and unambiguous. So altogether, my argument is that we should invest similar level of funding, billions of dollars in both approaches in order to hedge our bets. We don't know what would be easier to find. And the important thing to realize is that new evidence doesn't fall into our lap. We have to really spend money on the search. Now, there were several reports from the Director of National Intelligence to the US Congress talking about unidentified anomalous phenomena near Earth that the military personnel and the intelligence agencies are finding. And the point of the matter is it's a serious matter if we are dealing with human-made technologies that produce those unidentified objects, because then it means that it's a matter of national security, and those intelligence agencies are not doing their job. So even though the 2026 defense budget would be $1 trillion, they seem not to figure out everything that flies in our sky, and that's really a big problem. Alternatively, it could be some extraterrestrial visitors, and obviously that would be of great significance scientifically. So we better assess what the origin of these objects is. And I decided to lead the Galileo project over the past 3.5 years, where we are constructing observatories that are collecting scientific quality data on unidentified objects in the sky. And we have infrared visible light cameras covering the entire sky all the time. And then we use machine learning software to analyze the data. So the latest observatory, I mentioned it in a podcast that I had with Joe Rogan just a week ago. The latest one is in Las Vegas on top of the Sphere. We went there this summer and installed it. And you can see here the Sphere. The Sphere is a construction with a height of about 130 meters, and it cost $2.3 billion to build. mostly for entertainment, but there is a great interest of the person who owns it, Jim Dolan, to communicate science to the public. And he came to my home and asked me to build this observatory of the Galileo project, one out of several that we have. And we did it this summer. We went up to the top of the sphere, and you can see here on the left the kind of difficulty we had. We had to make sure that we don't bump our head against all these steel pipes over there. And at the end, we were able to place a set of Galileo Project cameras on top of the sphere. You can see it here with the view of Las Vegas in the background. And so if you look at the sphere from an airplane now, and you will see a freckle on top of it. It's not entirely smooth, and it has an exosphere that with 17,000 LEDs. But our observatory is on top of that, and we have two other copies that allow us to do triangulation of objects in the sky to figure out their distances, velocities, accelerations. So altogether, we have three observatories, one in Las Vegas, two others, one in Massachusetts and another one in Pennsylvania. But what I would like to speak about most is actually a new frontier in astrophysics involving interstellar objects. And it's really a new window into the universe that can bring a scientific revolution to the way we do astronomy. These are objects that spent millions to billions of years arriving into the solar system from far away. And in principle, they give us an opportunity to figure out what lies in our neighbor's yard. And it could involve rocks of a type that we've never seen before, but it could also be technological gadgets that were sent by others, just like we sent the Voyager out of the solar system. So in 2014, the first one was actually seen as a meteor. It was an object that collided with Earth at a very high speed and was identified by US government satellites. 2017, a survey telescope in Hawaii called Pan-STARRS discovered Oumuamua. This name means a scout in the Hawaiian language. That was roughly the size of a football field. The meteor was roughly half a meter in size. And the Oumuamua was about 100 meters. But it was very anomalous because it had a shape of a pancake, most likely flat, and it was pushed away from the sun by some mysterious force without showing any evidence for gas or dust around it the way comets do. Then in 2019, there was a comet called Borisov, and that one looked just like comets that we're familiar with. All of these objects were identified as interstellar because they were moving at a speed that exceeds the escape speed from the solar system, meaning that the sun's gravity cannot bind them. And then finally, in July this year, a comet, an object was discovered called Atlas, 3I Atlas, because it was discovered by a telescope named Atlas in Chile. And that is being discussed a lot right now. In fact, 3I Atlas last week came closest to the sun on October 29th. And as a result of that, it behaved in very unusual way. It became bluer than the sun. It also became brighter by a factor of 5, and then it deviated from its gravitational path. And we are still trying to understand why. And because it's on the opposite side of the sun relative to Earth, we couldn't observe it when it was closest to the sun, but now we're starting to see it. So in fact, just today, I wrote 2 essays on medium.com, and you can check them out. Avi Loeb at medium.com, you can find the updates. We have images of 3 Atlas that show for the first time some jets coming from it. And there are about 7 of them, if not more. And that's remarkable. That's just very recent as of today. Before that, the Hubble Space Telescope, you see the image on the right, show that there is actually the brightness around 3A Atlas is elongated in direction of the sun. And that's, again, not common. We haven't seen it for comets because usually there is a cometary tail where the gas and dust are pushed away from the sun by the solar radiation and the solar wind. And moreover, the Webb telescope implied that the gas around it is mostly carbon dioxide, very little water. And in addition, there was nickel discovered with very little iron around it. And that is very surprising, never seen before, only seen in industrial production of nickel alloys. And therefore, the question arises as to whether this object is technological. And this question is primarily motivated by the fact that the object is very big. It's a million times more massive than the first interstellar object, Oumuamua. And also it travels in the plane of the planets around the sun. You can see the trajectory at the bottom of this slide. And you can see 3A Atlas is coming into the solar system along the plane of the planets, the ecliptic plane. So that raises the question of whether it was sent by some intelligence for a reconnaissance mission, or maybe it's a mothership that would release some probes into the solar system. I will not get into all the details. I'll be glad to answer any questions you have. There are 10 anomalies of this object, and meaning that there are 10 aspects of it that are not familiar from previous comets that we know about from the solar system, or even the interstellar one that preceded this one. And so the fundamental question is whether it's natural or artificial. And we cannot ignore the possibility that it's technological simply because the implications would be huge. So even if we assign a small probability for it, it's important to check whether that may be viable or not. It's like it could be a black swan event. And I defined a scale a few months ago. Now it's called the Loeb scale, where 0 means definitely a natural object, and 10 means a technological object that could be a potential threat to humanity. And in the past, I ranked 3A Atlas as somewhere between 3 and 4. And I'm waiting for the data that will come in the coming weeks. And after we know much more about it, I will update my ranking. It will come closest to Earth on December 19th. And so that's, let's just hope that it will not deliver any unwanted gifts for the holidays to Earth. And then I'm very grateful to Representative Anna Paulina Luna that actually urged NASA to use a spacecraft that is orbiting Jupiter in March 2026, when 3A Atlas will come very close to Jupiter. On October 3rd, it came very close to Mars, and we haven't seen the data that NASA collected from the high-rise camera because of the government shutdown. This is a camera that is situated on board the Mars Reconnaissance Orbiter, and it should give us the highest resolution image of 3A Atlas, but unfortunately we haven't seen. It should give us a 30 kilometers per pixel resolution. So I very much look forward to seeing it once the government shutdown will be over. The fundamental question is what to do the day after we discover a technological visitor. And there are lots of items here. I will not get into them. But this object 3A Atlas had, as I mentioned, 10 anomalies. And it's not the first time. The first object, Oumuamua, had other types of anomalies. It was most likely flat, a very extreme shape based on the fact that the amount of sunlight that was reflected from it changed by a factor of 10 as it was tumbling every 8 hours. And the best model was that of a flat object, pancake-like. And it also had some excess force, push away from the sun without any cometary tail that you would expect from the rocket effect from evaporation. And I suggested that it's just the sunlight pushing it. And in fact, 3 years later, there was an object discovered by the same telescope in Hawaii that was pushed away from the sun by reflecting sunlight, and it ended up being the upper stage of a lunar lander that was launched in 1966, and it was a hollow rocket booster that was pushed by reflecting sunlight. So we know that because we launched it. The question is, who launched Oumuamua? And we know that that there are not only rocks out there in space because we polluted space with technological gadgets. In fact, on January 2nd this year, the Minor Planet Center announced a new asteroid and gave it a name, near Earth. And then they realized, oh, wait a minute, it's actually moving along the path of the Tesla Roadster car that was launched back in 2018 by SpaceX as a dummy payload on the Falcon Heavy. So then they removed it from their catalog because they realized it's not a rock, it's not an asteroid, it's a car. And the only reason they knew that is because there is a documentation of the kind of technological objects that we launched to space. However, if someone else in the galaxy launched something, they would obviously misclassify it as a rock or a comet. So there are many examples of that. And right now, for example, Oumuamua is regarded by comet experts as a dark comet. And that's because they specialize, their vocabulary spans mostly comets. Their training data set, just like LLMs, is comets. And so they call it a dark comet simply because it doesn't show a cometary tail. But that's the signature of a comet. If you don't see the signature, why would you call it a comet? After all, if it were a spacecraft or a technological gadget, it obviously will not have a tail. So it's the same situation as if there is a scholar that specializes in zebras and then sees an elephant in the zoo and would call the elephant a zebra without stripes. It's not a zebra without stripes. It's a completely different animal. And the same is true about technological gadgets. And we shouldn't call anything that doesn't behave like comets a dark comet. I mean, if it doesn't have a tail, we should be worried that it might not be a comet if it shows, for example, non-gravitational acceleration. So the next Copernican revolution would be that not only that we are not at the physical center of the universe, we are probably not at the intellectual center of the universe. And the point to keep in mind is that most stars formed billions of years before the sun, and it takes Voyager less than 1 billion years to cross the Milky Way galaxy. So there was plenty of time for technological gadgets to reach our backyard from anywhere within the Milky Way galaxy, assuming that other civilizations evolved on a time scale similar to intelligent life on Earth. Now, about 2 years ago, I decided to lead an expedition to search for the materials of the interstellar meteor that was identified by US government satellites back in 2014. And it exploded 20 kilometers above the Pacific Ocean. And the US Space Command sent an official letter to NASA confirming what we argued in our paper, discovery paper, that this meteor is of interstellar origin at the 99.999% confidence. And they also released the light curve of the fireball, and there were 3 flares. And this meteor was moving at a speed similar to 3I Atlas outside the solar system of over 60 kilometers per second. And so I wanted to check whether we can find evidence for whatever remained from it after it exploded. And so I led an expedition to the Pacific Ocean. That's the deck of the ship that we used. It was called the Silver Star, and we went there for a couple of weeks. And here you can see the method that we used to pick up materials from the bottom of the ocean, which was 2 kilometers deep. And we built a sled with magnets on both sides. And this expedition was actually filmed by a Netflix crew, and you can see them on the bottom left and middle. And I usually jog every morning at sunrise, and I did it also on the ship. And one day they decided to film me, and the director asked me, Avi, it looks like you're running. Are you running away from something or towards something? And I said both. I'm running away from some of my colleagues who are not seeking evidence because they think they know the answer in advance. And I'm running towards a higher intelligence in interstellar space. So this is us working on the sled. Every time we put it on the ocean floor, we collected some materials, brought it back to the deck, and checked the magnets on it to see if there are any magnetic particles that were trapped. And at the end, I shipped the very little material that we found in this black suitcase on the right-hand side here, and brought it to the laboratory of my colleague at Harvard, Stein Jacobson. And on the other side of me is a summer intern, Sophie Bergstrom, who found 850 molten droplets in the materials that we brought back. And you can see that these molten droplets are very distinct relative to the sand from the ocean floor. We could pick them up with tweezers. And then out of the 850, about 10% ended up being unusual in their chemical composition. And in particular, what you see here is the abundance of various elements from the periodic table. Oops, I'm not sure why it's jumping. Not sure. So anyway, what you see here is the abundance relative to the standard solar composition. So 1 in the vertical axis means solar composition, and the horizontal axis shows different elements as a function of their volatility. And so elements on the right-hand side are very volatile. Indeed, we missed them. They were lost in the explosion. So these particular spherules or molten droplets are likely to have originated from a meteor. And there are some elements that are up to 1,000 times more abundant than solar system materials, elements like beryllium, lanthanum, uranium. And so we called it Belau. This kind of abundance pattern was never reported in the scientific literature, and it was never found from solar system objects. And so we think maybe it's evidence that we found some remnants of the original interstellar meteor. But of course, that abundance pattern could be produced through a natural process. And I actually published a paper suggesting that the disruption of a planet like the Earth near the most common type of star, a dwarf star, could account for this unusual chemical composition. But we don't know the nature of the original object, and we hope to go there again and collect bigger pieces. And we are currently seeking funding for that. We will use a robot that we will place on the ocean floor that would give us a view of what is there, and it would pick up bigger pieces of the original object, hopefully. Now, in June 2025, this year, a new observatory was inaugurated in Chile. It's called the Rubin Observatory, that was funded by the National Science Foundation and Department of Energy. And it can detect interstellar objects every few months. It has an amazing camera of 3.2 gigapixels. And it started operations, and now they are still working to make sure the equipment works, the data transfer works, and hopefully within a couple of months we'll start getting data, and together with my postdocs we will look for new interstellar objects and try to see if there are any different than the previous ones, because there is always a chance that one of them will not be a rock, but instead a tennis ball that was thrown by a neighbor. Thank you. I will stop here and take any questions you have, and I'll be glad to elaborate on some of the items more than I mentioned.
If I could touch base on that last chart that you just showed, there was a question regarding the abundance patterns that you were noticing in the material that you were gathering. Is the purpose of that to try and identify it as extrasolar in origin, to further identify it as unique from other extraterrestrial materials that have been investigated as well?
Aside from solar system materials, the only other particles that were analyzed from interstellar space are dust particles. And this is very different from dust particles because we are talking about a big object. Usually such objects are produced in planetary systems or maybe other environments that we are not familiar with. And in particular, in the case of 3I Atlas, we are talking about an object bigger than 5 kilometers. So far, we know that it's at least the gas that came out of it is mostly carbon dioxide, 87% by mass. So it's definitely not the composition of solar system comets that are rich in water. And the question is, was it produced in a protoplanetary disk, the way that we would suspect based on what we know about the solar system? Now, other than dust particles and, of course, the latest interstellar objects, we don't know what is the composition of objects that enter the solar system far away. And so we wanted to, first of all, verify that we found some material that is not from the solar system. And indeed, the chemical composition that we found is unique. It was never reported before. But that's by itself not sufficient. We would like to analyze isotopes. We just didn't get a large enough sample to have a definitive result with respect to isotopes. But if we get bigger pieces, they would allow us to clearly separate solar system materials from materials outside the solar system, because those isotopes originate from a supernova explosion, an exploding star that would be different in different parts of the Milky Way galaxy. And therefore, we could tell that the material is coming from a completely different origin. And then there is the whole question of a technological origin. And for that, again, we need bigger pieces so that we can see the material structure, the solid state, the structure. Just think about throwing your laptop into a fireplace. If you just melt it into droplets, you wouldn't be able to tell that it was a technological device and not some material somehow that arrived into the fireplace from somewhere else. But if you do have some piece of the laptop or computer, then you would be able to tell that. So we are hoping to find bigger pieces in the next expedition that would give us a much better understanding. Now, speaking about interstellar objects, there the opportunity is far greater because we had the OSIRIS-REx mission to land on the asteroid Bennu and bring 120 grams of it to Earth. And over the past year, this sample return was analyzed, and we found that it contained most of the amino acids, the building blocks of life as we know it, from the asteroid. If we could do the same on an interstellar object, even if it's a rock, it's an amazing opportunity for astrobiology, for us to figure out if the building blocks of life as we know it exist, in rocks from another star. That, it would take us millions to billions of years to go to other stars, bring materials and analyze. It's much better to rely on objects that made the journey arrived at our backyard, and we can examine them. And of course, if one of them is technological and we land on it, we will immediately be able to tell that it's technological because it might have buttons on it. And the only question would be whether we should press a button.
Well, I personally will be very interested in the macro structure of any new materials that you recover on your project.
Thank you. Yeah. So we are currently, we can't do the next expedition because we didn't receive a donation that would allow that. It will be probably $6.5 million if we get it. But the previous expedition retrieved, tiny spherules that are less than a millimeter in size. So we're talking about milligrams, maybe, tens of milligrams of valuable material, which is not enough to do a thorough isotopic study, and definitely not for any material study. So, yeah, we really need to go again, or there is another interstellar meteor that landed near Portugal that we can go and search for any materials there as well.
I have one particular topic that's of interest because it's in the media currently. You've been making a lot of media visits talking about the 3I Atlas comet. Now that we have gotten data from post-perihelion approach, is there enough information to determine what the nature of the non-gravitational accelerations that we're seeing in the object are? And is there enough information eventually to be able to determine what type of average load would be required from any kind of deceleration to explain those deviations from non-gravitational behavior?
Yeah, that's an excellent question. So, first of all, I should say I have a place on medium.com. So if you search for Avi Loeb at medium.com, you can find my essays there. And a week ago, I did a calculation when the non-gravitation, I was announcing the non-gravitational acceleration that was reported by the Jet Propulsion Lab in Pasadena, NASA's. That was announced, just a week ago or so. And I immediately calculated, if it's a natural comet, you can just use momentum conservation and figure out how much mass did the comet have to lose, which fraction of the mass did it have to lose in order to gain this non-gravitational acceleration through the rocket effect. And there is an upper limit on the speed by which you can launch material from the surface of a comet, which is the thermal speed of the molecules there. And we know the surface temperature based on the distance of the object from the sun. So basically, we know the highest speed that material can leave the object, and then we know the acceleration that it encountered. And so the speed divided by the acceleration, which is the acceleration is just the time derivative of the speed. So the speed divided by the time derivative of the speed of the speed of the object can give us the characteristic time scale to ablate the object. And I found that it's 6 months. And then the object spent about a month at a distance comparable to the closest approach distance. And so it lost about a sixth of its mass. And the non-gravitational acceleration was revised a few days later. By 30%, it was brought down. And so altogether, I got a minimum of 13% of the mass, the initial mass of if it's a natural comet, that had to be lost in order to give it. That's a minimum because, sometimes, in fact, from the image today, and let me show you that image, it looks like it's not losing mass just in a preferred direction towards the sun. It's losing mass in all directions. Let me just share this image with you. This is an essay that I put on medium.com this morning. There are two of them, actually, because there was also a reported detection of OH molecules in the radio. So look at this image. This was taken just this morning. Okay, it's completely new. And so it shows these jets. For the first time, we've never seen these jets. There are 7 of them. And the direction of the sun is towards the lower left corner. Okay, so that's where the sun is. And indeed, you see some jets in that direction, but you see jets on from the other side as well. And it's clear that the mass loss is not in necessarily just one direction. And so that would actually make the fraction of mass that had to be lost much more than 13%. It should have been a fair fraction of the mass of the object, given that the jets are oriented all, they're all around it. And the question is there a very massive cloud of gas around 3I Atlas right now that accounts for a substantial fraction of its mass? Because that would be the prediction for a natural comet, given the non-gravitational acceleration that was measured. And that we can find out in the coming weeks. So we don't know yet because it just came out from the direction of the sun. So today it's about 30 degrees away from the sun in the sky. Before that, it was closer to the sun than 30 degrees, and telescopes cannot look so close to the sun. They get blinded by the very bright sun. So we just couldn't get much data over the past month, but starting today, actually, we are able to. So we should see whether there is a very massive cloud of gas and dust around it. And in that case, we will know what the object is made of. That would be easy. And we would clearly know that its nature is a natural comet. But if, on the other hand, there is no such massive cloud, then might be some other means of propulsion. Maybe there is some engine that gave it the non-gravitational acceleration, or these jets are thrusters on a technological object. We just have to wait for more data.
Given the mass that's still in proximity to the object, does that act as a system, or is it independent once it's left the main body of the object?
No, once it leaves the gravitational potential well of the object is very, very small, very shallow. So as soon as material leaves it, it escaped the gravity of the object, and it's only affected by the gravity of the sun. So there are tidal effects. If you consider an element of gas that is displaced from where 3 Atlas is, there would be some tidal effects separating them. And also there would be additional forces like the radiation pressure from the sun and the solar wind that are exerting an extra force on dust or gas particles. That the force is much weaker on a massive object simply because the bigger the object is, the less surface it has per unit mass, because the mass of the object grows like radius cubed and the surface area grows like radius squared. So small particles have a large surface for their mass, and big objects have very small surface for their mass. So that means that if you have a force that is acting on the surface, which is, for example, the radiation from the sun or the solar wind, it would much more easily push tiny dust particles or molecules than it can push a 5-kilometer nucleus. So the big object is not affected by these forces, but whatever leaves the object, gas and dust, will be pushed very effectively. And so that's what separates cometary tails. They usually go away from the sun because of these additional forces. And we should be able to see those if indeed there is a massive cloud of gas. I mean, that would mean the object lost a lot of its mass, and there would be no doubt of what the object was made of, because now it's destroyed, so to speak.
Thank you for answering that. Another question refers to the, let's just say, lack of acceptance for clear evidence that uncharacteristic behavior is occurring in this object. And in specific, could you talk further about both colleague and international response to these unusual behavior that are being identified?
Are you referring to interstellar objects or UAPs?
I'm talking specifically about Three Eye Atlas in this case, but you could also extend it to the UAPs that you've also discussed.
Yeah, so I guess the question is, why aren't other scientists willing to deal with anomalies? Is that the question?
That's pretty much it, because
Yeah,
clearly we know what we're seeing with regards to those things that have been
right.
made visible to the public on
Yeah,
UAPs, and we are seeing the behavior of Three Eye Atlas, both
right.
of them being anomalous in nature.
Yeah. So this is more a question for a psychologist than for me, but I would argue that experts, people that um, get their self-esteem and their stature, professional stature, out of the profession that they mastered over the past decades, they tend to explain anything in terms of past knowledge because they don't want to take any risks of being wrong. And they live in an echo chamber where they used to advocate some ideas and they want these ideas to hold. Any new knowledge is threatening their ego in a way, and they would resist it. So, before 1803, the experts thought that there couldn't be any rocks falling from the sky because we see rocks on the ground. But then there was a meteor shower in Liège, France, and a very distinguished physicist, Bayot, French physicist, went there and collected evidence and convinced the scientific community that indeed rocks can fall from the sky. And of course, in retrospect, that makes sense because the building blocks of planets like the Earth are just like Lego pieces. They still exist as debris in the Milky Way galaxy, but also in the solar system. And every now and then a rock collides with Earth, and that's what we see as meteors. Okay, so now that was accepted, since 1803, and there are comet experts, asteroid experts, and they insist that everything in the sky must be rocks. Why? Because they develop their expertise this way. Now, if there are anomalies, the way they respond to that, I'm talking about the professionals who practice science. I'm not talking about the influencers like Neil deGrasse Tyson or Brian Cox. These guys are just commentators. They don't, just think about them as people sitting on the bench and talking about what's going on in the field. The field like a soccer field, and they are not players. They haven't written a single scientific paper, these commentators. They're influencers. I don't really care much about these guys because they will always try to be popular. They will never dare to, pioneer a new scientific frontier or do any innovative scientific work. So they are completely irrelevant for the scientific process. But there are a lot of scientists who resist and they basically want to protect their stature, protect their funding. They don't want others to suggest that they missed something important, so they would, you know, um, rebuttal it and try to criticize it and ridicule thing. And for example, let me give you an example of something that doesn't make any sense. It's the fact that more than $10 billion are allocated to the search for microbes, where zero federal fundings are allocated for the search for intelligent technological objects or intelligent signatures and in space, and that makes no sense if you think about it, because as I mentioned, the signal could be potentially much greater, and unless we invested those billions of dollars, we would never know if we are missing something. So it's just a matter of convention, and sort of the mainstream adopted one variant, but it makes no. I mean, common sense argues that since the public cares so much about this, and the public funds science, that this should be a main theme of research, but it's not. And once we find that an interstellar object is technological, of course, all of these people that object to the discussion, we say we said it all along. This is nothing new, and it will become like part of the mainstream. That's what happened with the discovery of exoplanets. Um, when I started astrophysics. Uh, Most of the leaders of the field were arguing that the exoplanets are a complete speculation. We don't know if other stars have planets like the solar system and so forth. So, it repeats in the history of science that you have those experts that gained status and therefore don't want to give it up for new knowledge. And the problem with science is that you need to take risks in order to make big discoveries. You need to be humble to allow yourself to learn something new. So the foundation of science is uh, the humility to learn and not the arrogance of expertise. But unfortunately, what you see in academia is the arrogance of expertise rather than the humility to learn. And that's because the practitioners are putting their ego ahead of figuring out nature. And there is an excellent example for that. If you look at the theoretical particle physics for the last 50 years, since I started doing physics, they are obsessed with string theory, and there is no evidence whatsoever that any of the ideas that are expressed in string theory are relevant to nature. But they are just doing it as an intellectual exercise and, to show off that they are smart. And the only thing that counts, how do you separate a good physicist from someone who is not as accomplished in a field that has no feedback from experiments? You do it by who can impress you by mathematical gymnastics, but that's not physics. Physics is supposed to help us understand the reality, the physical reality that we live in. And if for 50 years you made no contact with reality, then sorry, you're not doing physics. And this is the mainstream of theoretical physics right now. So how do we explain that? It makes no sense. I usually argue that common sense is not common in academia. I mean, of course, there are lots of technocrats, people that drill, once they have a problem, they can solve it all the way down to the bedrock. If you give them a problem, that's what they would do. But what I'm arguing is about the architecture, so when you build a building, you can have a lot of people that know how to put bricks. Okay, so that's most scientists, they know how to put bricks, but someone has to look at the construction and ask, does this make sense? And otherwise, you get some very crazy, not very efficient structure that is not serving any good purpose. And you find those structures in science right now dominating the landscape. Like string theory dominating theoretical physics makes no sense. You find in astrobiology just the search for microbes, zero attention and actually a lot of ridicule towards the possibility that we are not necessarily the smartest in our cosmic block.
I know we
Yeah.
have limited time in interest of your time. I'm going to try and combine a number of things together in
Okay,
one.
go
So bear
ahead.
with
Go
me while I try
ahead.
and put that.
Yeah.
So you're working on the Galileo project, looking for extraterrestrial sources. Um, Dr. Stephen Hawking was notorious for his insistence that anybody that we would come in contact with in the universe is going to be advanced beyond us on the Kardashev scale. So you have that dilemma, that moral dilemma. Is it good to send out a calling card or to stay quiet? So first of all, for the people who are here, can you clarify, is the Galileo project only passive in terms of doing a sky survey and receiving information? And then secondly, what are your feelings about that with regards to, you mentioned a number and showed a slide of a number of extraterrestrial objects, sorry, extra solar
Interstellar.
objects.
Interstellar, yeah.
Yes. How
Yeah.
are we looking for those items that could be coming into or potentially even posing a threat to us? Because some of those diameters were quite small.
Yeah, that's an excellent question. So first about Hawking's point, unfortunately, nobody listened to Hawking, and we were transmitting radio signals for a century now, and everyone within 100 light years from Earth knows about us. And one possibility for a technological visit is that, it's the dark forest hypothesis that aliens are not very far and they're just watching us. They don't make a sound, as if they are in a dark forest where they're worried about predators. And with respect to the Galileo project, that's exactly right. That was my philosophy from the beginning, not to transmit, but not to be active in the search, but rather just search for passively for any signals. So this is indeed what we are doing.
And so what are the tools that we have to see these items as they're approaching us at a distance where we could take better action if there were such
Yeah,
indicators?
so that's a very good question. So right now we have the Rubin Observatory in Chile, and it will survey the southern sky every 4 nights, and it would be a good alert system for the southern sky. But we need a copy in the northern sky, and that would require an investment of maybe similar amount of money of the order of 800 million or so. We need to do that because otherwise we're missing half of the sky. But in the longer term, suppose we discover a technological gadget. My point is it will change everything. Then the politicians, the financial sector will pay a lot of attention because it will pose a new threat. As long as we can survive the first encounter, it will pose a new threat, and we will need an alert system. And my assessment is that right now we invest $2.4 trillion a year in military budgets, and we might decide to allocate a fair fraction of that to defending the Earth. And that would mean $1 trillion a year. And with that budget, we can, in principle, do a lot in space. We can build a lot of interceptors and sensors that would alert us to incoming objects and perhaps intercept them or get closer to them to send us high-resolution images so we can tell what they are. And also, I can see in the long term, if we detect other civilizations that travel through interstellar space, we might be inspired to imitate them because Oscar Wilde said imitation is the sincerest form of flattery, and we might give them a compliment by trying to resemble them. It's like finding a sibling that is more accomplished than you are, and it would give us inspiration. And my hope is that it would convince us that what we are doing right now is a lot of wasted energy, resources, time in fighting each other on this rock that we were born on. If you read the news every day, it's very disappointing to see people engaging in conflicts. And the way I feel about it is like being in a party where the attendees are misbehaving, and the only hope I can have is that a new guest will show up that will change the situation.
To the Northern Hemisphere blind spot, what is lacking currently in the Mauna Kea system?
Oh no! So you have to understand that most telescopes are looking at a small portion of the sky. They don't do a survey across the entire sky. So you need a special camera of the type that I showed you at the end that a survey telescope uses because it has a large field of view and then it tiles the sky. It goes from one part of the sky through all the sky, and in the case of Rubin, it does it every 4 days. So it tiles the entire sky. So you need something that covers the entire sky. We don't have it in regular observatories that we have, like, as you said, Mauna Kea or any other telescope. These are telescopes designed to look at very narrow parts of the sky and look very deep. And what we need is something, a survey telescope that is a completely different architecture in terms of the instrumentation, but also the data analysis. The amount of data flowing in from the Rubin Observatory is unprecedented, never before, because it has 3.2 gigapixels in each image that takes 30 seconds. You get a huge amount of information.
So it's really as much an astronomy question as it is a data consumption and processing question.
Yeah, so it's a question of priorities, and I think I would advocate putting a northern copy of the Rubin Observatory. But then, if we do find a technological visitor from outside the solar system, I think the level of funding will have to go from $1 billion to $1 trillion a year, because at that point, citizens and financial markets will be volatile to a potential threat from space. I mean, governments cannot protect us right now from any. I mean, we would feel as if we are, at the mercy of whoever visits us. That's not a good situation to be in. We will need an alert system, and then have policymakers work together with scientists to figure out how to respond to that.
So I think all of us have a responsibility to at least broach this topic with all of our friends.
I believe so. It's better to do it before the first encounter, but practically speaking, I think the political interest will come after the first encounter. But once again, there might be a lot of traffic already. We just don't notice it. And so that's my goal right now is to look at anomalies and see if any of them is convincing as a technological signature.
Thank you so much, Dr. Loeb. It was a very interesting talk. We appreciate your insights, and we wish you lots of new discoveries, both undersea and out in the space.
Thank you for hosting me. The questions were excellent. I really appreciate that. I'm glad that I left half of the time for that. Thank
Very
you.
good. Thank you for your time, everybody.
Bye-bye.